Welcome back, everyone. In this video, I'll be going over the lecture for graph sketching. Now, as far as this lecture goes, really what we're going to be doing is we're going to be putting together a lot of things that you knew before the class, but we also talked about in the chapter 2 when we were talking about limits, and what we've done in this chapter, which is on the derivatives and the sign chart, and then using L'Hopital's rule to figure out limits at infinity that we could not do before. So that's really what we're going to be focusing on. One thing I like to mention before going into the problems is that there are a lot of steps to these problems. At the end of the day, the goal is really, if you're looking at a graph, can you identify the important things? We're just going to be starting by graphing it. And then as we graph, we need to know what increasing, decreasing, concave up, concave down, all that stuff means to be able to graph it accurately. So we're going to be practicing those skills while we learn how to graph these. And really the most important thing is you get a general idea of what a graph looks like based on the information you figured out. It doesn't have to be perfect because really it can't be. We've talked about why it can't be before, but we're going to just really be doing what I just said. So one thing I'll really stress is that when I go over the guidelines for how to sketch a curve, you've learned a lot of these over many years of math. The first half that I go over are going to be things that you've done before calculus. And then the last half are going to be things involving calculus. So it's going to be a lot of little stuff to be able to graph with as much possible precision as possible. But at the end of the day, once again, if you can do each individual parts of these, and then you can look at a graph and know, okay, this matches what my information says. I figured out it's increasing on this interval, this graph matches this, and it's the only one that works, then that has to be the right thing. But with that said, you do want to, at least when practicing and going through the lecture, try to make sure you can understand every part. All right, so when needing to graph a curve y equals fx by hand, it is important to follow some general guidelines. And basically this list of guidelines, the more stuff you learn about math, the more precise you can be about graphing by hand. So that's why this list is so long. The first thing is probably the most important thing though. If you don't do this, then it's impossible to graph it. And you need to find the domain of your function. Now we talked about the domain and a similar idea of continuity in the first chapter. So just kind of remind you when we go through a problem, what things you're looking for. But the domain of functions, we can't have negative numbers under even root radicals. We can't divide by 0. The domain of a logarithmic function, the inside must be positive. So if you see any sort of issues like that, it's going to affect your domain. And the big thing is that if you don't know the domain, even if you figure out everything else, you can't possibly graph it because you're not going to necessarily be graphing the correct part. Right. Number 2 is find the intercepts, and I write if possible. So the reason why this is an if possible, the y-intercept is usually straightforward, but x equals 0 has to be in your domain. Because how do we figure out a y-intercept? Well, a y-intercept's what the number is when we plug in x equals 0. So this is hopefully just a reminder. You plug in x equals 0 and you get a y value. That's your y-intercept. However, if x equals 0 is not in the domain, then you can't plug it in. So it doesn't necessarily exist. Well, the x-intercepts, they don't have to exist either. You don't have to have any x-intercepts, and you have seen tons of graphs that don't have any x-intercepts. And if they do, even if they do exist, it can be impossible by hand. Now, if you can do them by hand, it does help you graph them. So you don't want to just say, oh, I don't want to do the x-intercepts, because they can help shape your graph and make your graph more accurate. But in general, we'll see kind of a problem where you're really not going to be able to figure them out by hand, and that's okay. But remember, for x-intercept, you plug in y equals 0. And you hope, although you don't have to, and you might not be able to do it by hand, but you hope to get x values. But once again, there doesn't have to be any x-intercepts, so you might not get any x values. There could be 10. Maybe you can figure out all 10 of them by hand, and that's great. You might not be able to figure out any of them by hand, so that's why I wrote hope. That's what we hope to do. All right. Number 3 is a really optional because it's really hard to tell when you're looking at an equation, a function, just if it has symmetry. It's almost one of those things where after you graph it, you realize that you have symmetry. So I write optional for a reason. But symmetry, the reason it can help you is maybe if your graph is symmetric about the y-axis. That means if you graph the left half, you can go ahead and just use symmetry to graph the right half, and you don't have to do all the extra graphing parts. But the example I had down here was y equals x squared, and that's just the parabola. This is symmetric about the y-axis because if we take our graph and we flip it over the y-axis, then this part goes over here, and this part goes back over here. And formula-wise, the way you can figure out if something is symmetric about the y-axis is you replace x with negative x. So we would have negative x squared, and you can see it goes right on top. Now, in general, if you have a messier formula, this is harder to deal with. So that's why I say, really, it's optional. I don't ever really touch on symmetry unless if I start graphing once I figure out a whole bunch of stuff and realize, oh, wow, actually, this is symmetric, because it's not the easiest thing to notice. Okay. Now, there are also symmetries about the origin. You won't have symmetry about the x-axis because that wouldn't pass the vertical line test and it wouldn't be a function. All right. The other thing, this can be really helpful, is if your function has a period. Now, for the most part, unless if you have some very precisely defined functions that have periods or are periodic, pretty much the only ones are trig functions. You can definitely make some up by hand, but they would have to be very, very specific, and they're not going to be in this section. So one thing I want to go ahead and mention is that it has to be an only. If you have something else that's not a trig function with a trig function, it can sort of look periodic in the fact that its shape looks like it repeats, but it's not actually periodic. So I want to go ahead and describe the two examples I have down here. The first one I have is y equals sine of x plus e to the x. So notice that sine of x, of course, is a trig function, and e to the x is not a trig function. And what you'll notice is that, I'm going to scroll out here, e to the x actually gets big so fast that it kind of makes it look completely not periodic. Actually, let me go ahead and just for emphasis change this to x, but e to the x works as well, but it's a little bit easier to see. So with y equals sine of x plus x, this part is periodic just because it's sine of x. It's a trig function. And this part x is not periodic because we know the graph of x is just that line that goes up. It doesn't repeat itself. Well, you notice we kind of follow this wavy pattern, so the shape itself repeats itself. But to be truly periodic, the y values have to repeat. So this would have to go up, then eventually come back down, and then follow the same pattern. So it sort of looks periodic for parts as far as the shape goes, but it's not actually periodic itself. The only types of periodic functions that we have really, yeah, we could probably make some up by doing some weird piecewise definition, but it's only if you really have only trig functions. So sine of x minus cosine of x. There's actually an identity for this one, which is why this pretty much just looks like sine of x, but you'll notice that, or cosine of x, has the same shape. But really what's going on here is that this is kind of shifted, a shifted graph of sine or cosine. So notice that for one, the y values for regular sine and cosine only go between -1 and 1. So this actually isn't a repeat exactly. The y values don't follow that pattern, but it is a periodic function. It just rides this wave up and down, up and down. It's just going to have a different shape as you go through the period as far as what are the y values allowed to be. Right, but its period is 2 pi, and that's because the period of each part is 2 pi. Now, once again, you won't see a lot of things that are periodic because they have to be purely just trig functions. If you multiply trig functions, So sine of x times cosine of x, it's still periodic, but it's a lot harder to see because what's going on here is actually something that's related to a trig identity to make it simpler. So graphing this, even though it's not too bad, is not as easy as graphing something like this, or minus, I guess what I had. But the point here is that once again, trig functions, if you only have trig functions, it's going to be periodic. If you have trig functions, it can look slightly periodic. So that's something that's helpful. It's just not truly periodic. All right, and now that's all stuff that you have seen before this class. And you also may have seen asymptotes, but maybe not in the way it's presented here. So the next thing we want to look at is asymptotes. Asymptotes are, well, they have two categories. We have horizontal and vertical. Horizontal asymptotes are gotten if the limit as x goes to infinity of f of x or negative infinity of f of x are finite numbers. And we talked about how any function can have 0, 1, or 2 horizontal asymptotes. So any function can have 0, 1, or 2 horizontal asymptotes. We go ahead and write that in, horizontal asymptotes. We did have the very special example, which is very useful in that if it's a rational function, so a polynomial or over a polynomial, it can only have 0 or 1, so it can't have 2. And the reason why I point that out is rational functions are usually the main type of example of graph in this section. So I wanted to go ahead and make sure we specify that rational functions can only have 0 or 1 horizontal asymptote. It cannot have 2. So it's easy enough when you come to a rational function to only do the limit as x goes to infinity. You don't have to do both. Okay. Now, vertical asymptotes occur when either one-sided limit, so limit as x goes to c, it could be from the left or from the right, is infinite. And the way we really establish that, especially with rational functions, since once again, that's really our main example, is the denominator equals 0 for a limit, and the numerator does not equal 0 at x equals c. Now, there are other ways to get vertical asymptotes. We saw some in the previous section when we did L'Hopital's rule. We had an example of a function that was like cosine of x over 1 minus sine of x or something like that. It's not a rational function because it is not a polynomial over a polynomial, but we did have a vertical asymptote. But the main thing to look out for vertical asymptotes is because the denominator is being 0 and the numerator is not 0. When that happens, you're really looking at the x values when the denominator is 0. So for vertical asymptotes, we check when the denominator equals 0. If you don't have a fraction, it's very unlikely you will have a vertical asymptote. The one exception being the natural log, because the natural log function has a vertical asymptote at x equals 0. And I'll just very quickly remind you of that. So y equals ln of x has a vertical asymptote of x equals 0. That's pretty much the main example. The natural log function is pretty much the main example of things that can go bad and don't follow almost everything we do here. Right. Now, 6 and 7 are the things that should be pretty fresh in our mind, so I won't go into the details about that, but we want to figure out pretty much where the graph is increasing, decreasing, and if you have any local maximums or minimums. So we make the sign chart for f prime. And then we also make the sign chart for f prime prime to figure out where it's concave up, concave down, and if you have any inflection points. Right, so these are the new things. We won't go into details about those, but as we work through the problems, you'll just pretty much be getting more practice with all of this stuff. And that's one of the main things of this section, is just getting more practice. And the other thing is, putting that practice, putting formulas into a picture. Can you actually use the information to sketch the curve? And then based on the above information, you should be able to sketch it with some accuracy. Now, keep in mind, it's not going to be perfect, but when you look at the answer compared to what you've drawn, it should have a familiar, similar shape. If it looks totally different, then maybe, look back. Are you missing an asymptote? Look at this asymptote section. Are you missing where it's increasing, decreasing? Look there. If you have a messed up domain, recheck that. All right, so one thing I wanted to do before we actually move on to the problems is actually just go over a standard thing, is that the most common examples to graph are going to be polynomials and rational functions. Not always, of course, we will have some other ones, but these are the most common. And polynomials are very easy to standardize because they always have the same sort of thing. The domain of a polynomial is always infinity to infinity. Well, the intercepts of a polynomial, the second thing we would want to check, well, the y-intercept, you just plug it in, x equals 0, and you can solve for y and plot that. Now the x-intercepts you can usually find by factoring. You might not be able to factor it, and if you can't, you could use the quadratic formula, but you also might be in a situation where that's not valid. And so if you can't pretty much find the x-intercept by factoring or using the quadratic formula, you won't be able to find them, and that's okay. But the y-intercept is really important that you plot. Polynomials only have symmetry for very special cases. And in general, I wouldn't worry about them. Polynomials are not periodic, so they're never periodic at all. And you could have a polynomial that's just a number, so it's a horizontal line, which is kind of technically periodic, but that's just a horizontal line. Graphing that is very easy. Polynomials have no asymptotes, but vertical doesn't have any asymptotes because the domain is the infinity to infinity. It doesn't have any horizontal asymptotes because we know the limit as we go to infinity or negative infinity of a polynomial is always infinity or negative infinity. And once again, that's really because of how we did it in a previous section. So we don't have to worry about asymptotes for polynomials. Of course, the sign charts to figure out where it's increasing, decreasing, local extrema, concavity. Yeah, you're just gonna have to do that every time. And then you graph based on the sign chart and the intercepts. So really the main point here is that if you're given a polynomial, you really only have to worry about the intercepts and the sign charts to graph. The other stuff is not going to help you. Yes, there might be a symmetry, but you're going to graph it and then you'll notice the symmetry at the end. Right. So I want to stop this video here. I know we just talked in generality about what we're going to be doing. The reason why I wanted to do specifically this run through of polynomial is that I'm not going to do a specific example with a polynomial. So if you have one or you wanted to graph a polynomial, the point is you would look out for these main three things. But we're going to focus on an example dealing with a rational function and then something a little more challenging. So I'll see you in the next video.